Hello and welcome to this webinar by the Institute of Navigation. And good morning from the Washington, D.C. area, and good evening to Dr. Gao from his location in China. We welcome him. Dr. Han Gao received his PhD from the University College London in the Engineering Faculty's Space, Geodesy, and Navigation Laboratory. He received his bachelor's degree in aerospace engineering in 2014. He's interested in multi-sensor contextual navigation and positioning technologies. We welcome Dr. Gao and look forward to his presentation. And at the conclusion of his presentation, you'll be able to ask questions. You can put those, if you click on the Q&A icon, please feel free to put your questions in there. And Dr. Gao will address your questions at the conclusion of his presentation. So Han, over to you.
Yeah, thank you for your introduction. Hello, everyone. It is my pleasure to share my work on the webinar during pandemic. Today, I'm going to share my paper published on the spring volume of Navigation Journal this year, which is under the supervision of my supervisor, improving environment detection by behavior association for context-adaptive navigation. First of my presentation, I would like to talk about context. What's the meaning of context in navigation domain and why it is important for navigation? For navigation, the context refers to the environment that a navigation system operates in and the behavior of its host vehicle or user. Here are some examples: pedestrian walking on the urban street, car parking on the open land, and a UAV may flying on the sky. So why the context is so important for navigation? First, in terms of navigation, in terms of environment, it can determine the signals available for positioning. For example, for GNSS, it works best in the open sky environment. For our smartphone, it can achieve about 3-meter accuracy in an open sky environment, but degrees in the urban environment will not be available in most indoor environment. For visual positioning technique, it works best with in the environment with lots of features. The visual positioning would fail in an open environment because in such environment, it would not have, for Wi-Fi positioning, it relies on the Wi-Fi router. So it works best in the environment with lots of Wi-Fi routers, such as indoor environment. And for behavior, for example, with a pedestrian motion detected, we can apply the PDR algorithm for pedestrian navigation. And when the pedestrian is detected to be stationary, zero velocity and positioning updated can be applied. For vehicle, as land vehicles always travels on the ground, we can apply the sideway or the vertical constraints for vehicle navigation. And at the same time, cars always travels on the road. We can apply the matching algorithm to further improve. And nowadays, many navigation systems, such as our smartphones or vehicles, must work in multiple contexts, like indoors or outdoors, and they can be static or with different motions. So, to provide better location-based service, the navigation system is expected to provide more accurate and robust positioning service across different contexts. So it is required for the navigation system to first detect its operating context first. And then based on the detected context, the navigation system can select the appropriate sensors, positioning algorithms or filter designs based on the context for better navigation solutions. Here's a simple example. A person may walk from indoor to outdoor environment. The corresponding navigation system mode will switch from indoor positioning techniques such as Wi-Fi or Bluetooth to satellite-based navigation. And when the person may stop at a shop or wait for traffic, the static mode will be detected. Then the positioning solution will not be updated anymore. So here is the context detection framework. Features will be selected from the available sensors on the smartphone for both behavior and environment detection. Then the behavior or the environment features will go through the classification model to get the initial classification results. To take use the time domain relationship, we can apply the different time sequential filter to improve the behavior and environment detection. As we know that two aspects of context, behavior and environment, they are now totally independent. So the context association is considered to combine these two aspects of information to provide the final results of context determination for context adaptive navigation system. First, I'll introduce the behavioral recognition work. Different sensors in both time domain and frequency domain will be selected from the available sensors on the smartphone. They include accelerometers, gyroscope, magnetometers, or the barometer. Different behaviors covered in this paper include different human activities and vehicle motions. First, the selected features will go through the classifier to determine if the behavior belongs to human activities or vehicle motions. Then, in the human activity classifier, it will distinguish if the behavior belongs to static, walking, running upstairs or downstairs. For this belongs to stationary vehicles with the engine on, different moving buses, different kinds of trains. Next, I'll discuss the features. Plenty of features in both time domain and frequency domain have been selected from the available sensors. It's not always guaranteed that by adding more features, they will bring much higher classification accuracy. So it is necessary to select a feature from the available we have been selected to find their optimal feature sets for the best classification performance. And the feature selection algorithm we selected is the sequential full floating selection algorithms. And the major advantage of the SFS algorithm is that it can find the optimal feature sets based on the specific algorithm and the whole selection procedure to find the optimal feature sets can be done in a quite effective way. Here we can see the performance of each classifier. For the human vehicle activities or vehicle motions, it can achieve about 99% accuracy with only 4 features using the algorithm decision tree. For human activity classifier, it can achieve about 98% accuracy with 13 features using relevant vector machine. For the vehicle motion classifier, it can achieve about 91% accuracy with 27 features. After getting the results from the machine learning tools, we know that there's no perfect classification methods. we cannot have an algorithm that can always provide 100% classification accuracy. So after getting the classification results, connectivity is further considered to take use of the temporal information to further improve the behavior recognition performance. Here's an example. For instance, if a person wants to get on a train, the person cannot get on a moving train directly. They have to wait for the train to stop, then get on the train and wait for the train to operate again. So we are going to take use of this kind of information to further improve behavior recognition. Here it is how behavior connectivity is achieved. What the information by now we have is the measurement algorithm and the estimate from the last epoch. After smoothing method, the initial estimate at the current epoch can be obtained. By considering the estimates between two epochs, the last epoch and the current epoch, a transform matrix can be obtained. By considering the connectivity information, we can update the transform matrix. The connectivity is such that, for example, a person connected from a moving vehicle, we can give a very low probability because it is not likely to happen in reality. And for the connectivity that is likely to happen in reality, we can give such connectivity information relationship a much higher probability. So with connectivity information, the transform matrix can be updated. With the updated transform matrix, the estimates at the current epoch can be updated. By a rescale, the probability of each behaviors can be obtained. Here's an example experiment results by collecting from the London undergraduate trains. We can see from the figure that the black line indicates the ground truth. The trains will stop at the train station and travels between the train stations. The blue spots are the results we get from the relevant vector machine. We can see that there are some faulty detections, but after the connectivity mechanism we discussed just now, almost all the most misclassified samples have been corrected with the connectivity mechanism. So here is the behavior recognition part. For the environment detection, in this paper, we focus on the indoor and outdoor detection because for navigation in indoor and outdoor environment, they rely on very different navigation techniques. And in the previous literature, different local sensors have been tried for indoor-outdoor detections, including magnetometers, Wi-Fi signals, Bluetooth signals, light intensity sensors, and also the signal get from the cellular tower. In the previous literature, this local sensor or their combination have been tried. They can achieve about 80% to 85% accuracy, which is far from enough for a robust context-adaptive navigation. So in this paper, the highlights of our research is to explore if we can use the satellite signals for environment detection, and then we can consider the behavioral environment association, how to use the information from behavior recognition to improve the results of environment detection. And this is the framework of the environment detection. Different features can be extracted from the satellite signal received by the smartphones, and after classified by support vector machine and hidden Markov model, different environment can be distinguished, including indoor environment, intermediate environment, and outdoor environment. All of the process have been done in probability way, so that the later navigation mechanism can know the uncertainty of the environment detection results. How we model the environment, and in reality, the history of the environment of a user is not totally independent. Actually, the environment, for example, I'm staying in, rely on the previous epoch or previous moments. So it is the environment changes is actually highly time domain related. So to model this kind of relationship, we use the Markov model to describe the temporal relationship of environments using hidden Markov model. To build up a hidden Markov model, some pre-information some parameters have to be predefined. It includes the initial state probability that describes the distribution of indoor, intermediate, outdoor distribution at the very first epoch, the starting epoch. The transition relationship between the states, for example, the probability from indoor to outdoor environment, from outdoor to outdoor environment at the next epoch, and also the emission probability. In the paper, we used the results of support vector machine to describe the relationship between the observations, that is actually the features selected from the satellite signals, and to model the relationship between the observations and the states. The states are the indoor, outdoor, intermediate. That's how to model the emission probability. And we know that to further improve the environment detection, the context association is considered. In reality, behaviors and environments are now totally independent. Two aspects of context information, they are actually highly combined. They can be used to improve the accuracy of context determination. For example, for the land vehicles, it always travels on the ground, and for the trains, it is always travel on the tracks. And for plane or UAV, it will not likely to be travel on the water or on the sea. So this kind of information is take use of to improve the context determination. Here is the table we have determined from behavior recognition. Two kinds of information can be take use of for context association. So first is if the behavior is stationary. For example, if the behavior is stationary, the environment will not be changed anymore. And the second one is that different subject behavior belongs to the pedestrians or vehicles. But if the pedestrian or vehicles will have any difference on the environment, here's an experiment to validate their difference. So we can see from the figure that bits of data have been collected in an indoor environment in London Paddington Station. The left-hand side data is collected on pedestrian, and the right-hand the right-hand side data has been collected on the inside the train on the vehicle. They have been collected almost on the same time, about 3 meters away from each other. By comparing these two figures, we can see that from their distribution, the average of the pedestrian data, the signal strength, sin0, is much higher than the vehicle ones. So based on this difference, we can make the conclusion that different classification models should be applied for different pedestrians or vehicles. And here is the context detection framework by far, haven't adding any context association mechanism. And here is how to add the pedestrian vehicle association into our current model. After getting the behavior recognition results, if the motions belongs to a pedestrian or a vehicle, different features can be selected based on the vehicle model or the vehicle model. So after extracting different features, different features can be used further in training or testing in the pedestrian vehicle association. For the other association, static or moving association, it is applied by updating the values of transition probability within hidden Markov model. It is actually achieved by a linear combination of the identity matrix and the transition probability we have defined in the previous slides. Based on they can be connected based on the stationary probability. We can get that probability from the behavior recognition results. We test the proposed algorithms on pedestrian and their different scenarios. The scenarios include open sky environment in the park, urban environment in city of London, in indoor environment. The duration of the data collection is about 20 minutes for each scenarios. During the data collection, the participant can behaviors as usual. They can stop or wait for performance. 4 algorithms have been compared to test the performance and the different scenarios. First, the hidden Markov model, only the hidden Markov model, the detail of the hidden Markov model and how to model its parameters can be found in a paper published also on Navigation Journal by Paul and me. On the support vector machine alone, a combination of support vector machine and hidden Markov model, and the algorithms in this paper, a combination of support vector machine and hidden Markov model with in open sky environment, all 4 algorithms perform very good. So for hidden Markov model, support vector machine, and their combination, they can achieve very high accuracy, and with association, all of the samples can be distinguished correctly. In urban environment, we can see that for hidden Markov model and support vector machine, their performance are not very good. Their detection accuracy is about 85% accuracy, but their combination can achieve about 95% accuracy. This the improvement partially due to the better Markov model. Here is the performance in the indoor environment. We can see that although a support vector machine can provide very good performance in plenty of application, but in here, it only achieves 80% accuracy. But with a combination of hidden Markov model, they can achieve over 98% accuracy, and further with association improvement, all of the samples can be determined correctly. We also test the performance of the algorithms on vehicle. So here is the test route we collect the data on a bus from the right-hand side to left-hand side. In the middle of the route, the bus will stop at a station which is under the bridge. Under a bridge, it can be treated as an indoor environment. Here is the performance. First, the hidden Markov model, we can see that there are plenty of faulty detections, especially it failed to recover, it failed to distinguish the environment after getting back to outdoor environment from the indoor environment. And the SVM compare these two lines, we can see that SVM is able to detect most environment correctly, although there are some faulty detections. By comparing these two SVMs, a combination of SVM, hidden Markov model, with and without the pedestrian vehicle association, we can see the improvements by considering the pedestrian vehicle association. And further compare these two lines, we can see how the performance is improved by the stationary and vehicle context association. So finally, the best performance is achieved with a combination of support vector machine, hidden Markov model, their combination, by considering all the association with achieving about 90% accuracy. Finally, a quick summary of this paper. We introduced the context and why context is important for navigation. Context refers to two aspects. The environment determines the signals available for navigation, and the behaviors, on the other hand, can contribute additional information for positioning solution. And the motivation of context determination is ContextAdaptive Navigation, which is to determine the context first, and then based on the determined context, the navigation system can reconfigure its framework for a better location-based service. In terms of behavior recognition, it first classify by machine learning algorithms and further improved by time sequential filter. That's the connectivity in the paper. In terms of environment detection, we use satellite signal GNSS for environment detection achieved by a combination of support vector machine and hidden Markov model. We also use the behavior information to further improve the performance of environment. That's behavior environment context association. There are two aspects of association: pedestrian vehicle association and static moving association. Finally, under different scenarios on both pedestrian and vehicle, it can achieve about 95% accuracy for indoor and outdoor detection and about 90% accuracy on vehicle. Finally, I will introduce some future work to extend the research work in this paper. First, multiple sensors could be added into the current framework to provide a more robust environment. And with multiple sensors added, for example, Wi-Fi signal, cellular signal, or light intensity signals, a more flexible framework can be achieved to enable the user to switch on or switch off the sensors. So when a user would like to switch one or some of the sensors, the smartphone can still provide environment detection results for the navigation engine. Second, for the algorithm, more clever algorithm can be tried. Here are some examples: RNN, recurrent neural network, LSTM, or factor graph optimization. Besides modeling of the time sequential modeling for the environment changes, there was a try. Finally, the context, how to implement the context determination into context adaptive navigation for seamless positioning across different contexts. Here's an example. In practice, for example, for our smartphone, it would operate in different environments. In a shopping mall, Wi-Fi cross-sourcing or Bluetooth-based positioning would be the best option. And when the user get outdoor environment, the navigation engine would switch to satellite-based method in outdoor environment. And in urban environment, the navigation engine may try the 3D model-based GNSS. And in the open sky environment, such as in a park, the conventional GNSS would be the best option. And that's all for the introduction of the paper. Thank you all for the listening. And I think the next is the Q&A.
And we do have a question, which we'll have here. If you go to the Q&A tab, Dr. Gao, you'll be able to see that.
So one question from Florent. The question is that, what's your semantic definition of intermediate context? The second question is that the stop bus under the bridge should be considered as intermediate or no, or not. So for your first question is the definition of intermediate. With the detailed introduction of the definition of indoor, intermediate, or outdoor environment, the intermediate context is for the pedestrian motions. So that's why we have the pedestrian and vehicle association. They also have different environment category. The environment context is for the pedestrian, not for the vehicle. And for the definition of environment, it is definition as the transition space between indoor and outdoor. Also, it includes the environment when the user is very near to a building. So that's the definition for intermediate context. The second question is that why under the bridge for the bus is not considered the intermediate. That's because the intermediate is always very short for the vehicle. So the intermediate category is not a part of, it's not a kind of category for vehicles. For vehicles, only two contexts have been considered, indoor and outdoor. The second question from Stefan. Were there any restrictions on how users use their phones? The second question is that did they need to hold in hand or could put them in pocket. There's no specific restrictions on how to use their smartphones. For the behavior recognition, we collect the data by putting the smartphone in pocket. But if the smartphone is put in hand, it would be fine. And for the environment detection, there would be some influence. For example, if the user would like to put their smartphone in their bag or into their pocket, there might be some signal attenuation from the bags or their trousers. When putting in their hand, they have the best signal strength. And I think when they want to put the when the user would like to have a robust environment detection, they can train different models based on the location of the smartphones. Next, the question from Haosheng Xu. For features to detect the context, could we derive features such as signal strength, code delay, velocity from the signal processing of IF data? This is the first question. The second question is that could we use the visibility of the satellites to detect indoor-outdoor context, also for the environment such as deep, middle, slack, urban context? For the first question, you have a very good question. This is a direction to go, but in our paper, the only information we can get is from the Android API, the signal strengths, how many satellites we can receive. That's the information we can get from the Android API. So for more deep information, such as code delay, signal processing of the of IF, more information would be useful to improve the accuracy of environment detection, also for different kinds of context. The second question, the answer is yes. Actually, we used we can see from this figure that we actually used different features for environment detection. They include the signal strength, signal availability. That is how you describe in your question. How many we receive, and also based on the behaviors. If the object of the behavior is a pedestrian or different signals, some of the different threshold would be calculated for environment detection.
Well, we seem to have lost Dr. Gao's internet connection, but we thank you for joining us today, and we will have an archive of this available on our website. You can find that at ion.org/publications. There's a link for our webinars. We thank you for attending today. We, of course, thank Dr. Gao for his time and preparation as well. You may also want to check out the virtual ION GNSS 2020 meeting, which will be taking place online this year, and that you can find more information at ion.org/GNSS. Again, thank you for joining us, and have a nice day or evening. And we will have another webinar soon, and we'll be sending those out through our normal email channels and posting on our website as well. Again, thank you. Have a good day.